There we are. Okay, now we're recording. So yeah, so this is a brief explanation of what the topics are about, and I'm just going to talk. Circuitry is a study of circuit, like how to build circuits to evaluate logical functions or Boolean functions. For that topic, there's a whole bunch of stuff in chapter 12 of the textbook, which you can take a look at, that talks about like how to create Boolean functions to do things that you want to do, like control a set of switches or like add binary numbers together or whatever. And then it also gets into the topic of how to optimize the circuit to take up the least amount of space on a circuit board and like have the smallest number of different gates and that sort of thing. So that is a pretty cool topic if you are interested in computer hardware. The topic of proof in mathematics is basically just like sort of a philosophical study of what constitutes proof. What is the history of the concept of proof in math, and how is our understanding of that kind of shifted and changed? I kind of alluded to part of this issue when I was talking about mathematical induction, because I pointed out mathematical induction is a perfectly valid logical proof, but it often doesn't reveal anything. It doesn't really give you any intuition for why the statement is true. And so should a proof do that? Does a proof need to make you feel like you understand it when you're done, or just confirm that it's true? That's kind of a philosophical topic that you might be interested in. Levels of infinity, we got started with talking about like countable infinity and uncountable infinity, and this topic goes into that subject in a little more detail. This would involve what's that thing called we were just talking about the other day? The continuum hypothesis, which I made an optional part of the reading. Probability. So we've studied counting. By the way, folks, please feel free to interrupt me if you have a question or a comment here. I'll make sure I have the chat open. Yeah, so probability. We studied counting, but counting is the basis for probability. But probability is just basically counting, except you divide the number by the total, right? So like probability is just one step further along, where you like, hey, let's divide and get a fraction, and that's the probability. But there's tons of cool applications for probability. One of the main things that you might want to study in probability is a thing called Bayes' theorem. And Bayes' theorem, you may have heard of Bayesian logic. And Bayes' theorem is basically a way to update probability based on new information coming in. And it is, you may have heard also about Bayesian filters. Bayesian logic and Bayesian probability is a really important topic in machine learning, because basically, so I'm going to sort of like really I'm going to give you like a really surface level basic explanation of this, but essentially machine learning, AI, right, is going to sort of take in a bunch, it's going to learn based on looking at a bunch of data, and then it's going to take the data it has and guess, is that a picture of a dog? Yes or no? And it's going to come up with a probability of whether or not it thinks that's a picture of a dog based on its information. And if it gets it right, or if it gets it wrong, it is going to update its probability calculations with that new information. So Bayes' theorem is sort of the fundamental calculation that like a computer is doing when it's learning based on a data set. Okay, so that probability has that application, which is kind of cool. So also going off of counting, there are a lot of sort of challenging counting problems that involve different strategies, sort of like riffing on the idea of permutations and combinations. You can develop all kinds of other strategies for counting types of things. Like an example is something called a derangement, where a derangement is like a permutation of a set where no element in the set remains in the same location. It's a derangement is where like everything moves somewhere else. So it has to be reordering the elements, but nothing can stay in the same place. And when you add on that extra rule, it's like, well, now that's a lot harder to count. So that's just one small example of the type of like advanced counting strategies you can study. P and NP. P and NP, this is a huge topic. So we talked about complexity of algorithms, and that idea of like polynomial complexity and exponential complexity comes in. You can take that and study things called complexity classes, which are basically, it's like a study of how feasible is it for computers to solve a problem in a reasonable amount of time. And there is a huge important open question that nobody has solved yet in computer science, which is basically, is it possible to take these really complicated like algorithms that are exponential time algorithms, and is it maybe possible to solve them in polynomial time instead? That is a very crude explanation of that topic, but P and NP is a big open question. It's the sort of thing where if anybody ever solved the question of P versus NP, if it was solved, it has the potential to utterly break computer security and make all the computer security vulnerable. Because if someone discovered an algorithm that simplifies exponential time problems, then people would be able to use that algorithm or modify it to break the RSA encryption strategies, which rely on basically really hard problems that take a long time to solve. So that's an interesting topic. Related, of course, to cryptography. So there's some synergy there. Cryptography would be the study of that RSA encryption algorithm and other modern encryption algorithms that rely on like basically factoring really large numbers and like taking two really huge prime numbers, multiplying them together, and then using that as like a special code. So yeah, very popular topic. Prime numbers in general are interesting. You could do an entire project on the subject of prime numbers and the different results that the mathematicians have discovered over the years about prime numbers, as well as lots of open questions about prime numbers. There's a ton of open problems, like there's something called the twin primes conjecture, which has not been solved. It's one of these open questions where it hasn't been proven, neither has it been disproven, so we don't know if it's true. And there are computers testing the conjecture up to very large numbers, and they've never found any evidence to like say that it's false, but they still haven't proven it. So it's one of these like, you know, there's a lot of other open questions about prime numbers. So you could do that if you're interested. Recurrence relations. So when it comes to recursively defined sequences, like the Fibonacci sequence, like I was talking about earlier, I mentioned that there is a closed formula for the Fibonacci sequence. So you can take that recursive definition and you can do some math on it and solve for a formula where you just plug in n and get out the nth Fibonacci number. The process of doing that, of taking a recurrence relation between sequence terms and then solving for a closed formula, like an explicit formula for the numbers, that is what you could study in this project. That's pretty cool. Recursive algorithms is more of a computer science thing, where it's a study of different types of algorithms that use recursion in different ways. There's also, did I include divide and conquer algorithms in here? I didn't. Maybe I should have put that here. There's also another type of algorithm called divide and conquer, which you may have studied in a computer science class, and you could do a topic on that. That's in our textbook as well. Okay, so coming up after spring break, we are going to get into a topic called relations, And we're going to learn about a type of relation like less than or equal. Less than or equal to is a type of relation you can define on numbers, and it's a type of relation called a partial order. It's actually a total order. So there's different types of ways that you can take a set and define a relationship between elements of the set that puts it in order. And if the relation satisfies these certain properties, then it is called an ordering. And there is another big sort of unsolved problem, sort of. It's not exactly an unsolved problem, but it's more so like there's this thing called the axiom of choice, basically, which is one of the fundamental axioms that we use in mathematics, but it has a lot of surprising consequences that seem contradictory. Banach-Tarski is one of them. If anybody watched that video about Banach-Tarski that I sent out a little while ago, that one is sort of a seemingly contradictory result from this thing called the axiom of choice. And that is related to the idea of ordering and that any set can be ordered in some way. So there's all these connections. This is actually also related to the continuum hypothesis and levels of infinity. There's tons of interconnections between these concepts. So that's another very mathy sort of topic. So getting ahead, after we do that, we're going to study graph theory. Graphs, also called networks, are a very important topic for computer programmers because it's one of the fundamental types of like data structures, that and trees, which are basically a special type of graph. So chapter 10 is graphs, chapter 11 is trees. There's some cool topics you can do in here. The traveling salesperson is basically like a graph optimization problem, which is very hard to solve. And there are lots of algorithms for traversing through graphs in order to solve this sort of like optimization problem of what's the most efficient way to get through a network. Very relevant to computer programmers and data management and that kind of thing. Graph coloring is another topic which is useful for computer programmers and mathematicians alike. It's also, there's this famous theorem called the four-color theorem, which is an interesting historical example of, because it was the first theorem that was proven by computer-aided proof. And that was, at the time that they did that, it was controversial because people didn't really trust computers to prove things or like not make mistakes, I guess. But over time, that has become accepted in the mathematical community. So there's a little bit of interesting history in that subject. There's tons of applications of trees, ways that you can use trees as data structures. So you can do a whole project about that. Minimal spanning trees is kind of related to the traveling salesperson problem. It's again like a way to efficiently work your way through a tree structure. Another thing relevant to data structures and efficiency. And then in the end of the semester, we're going to get into chapter 13, which is going to introduce some more sort of computer science concepts like formal languages. One of the ways that you can define formal languages like C++ or Python or HTML or BASIC, right? Or machine code. Like these are formal languages that have these like not semantics, but like syntax grammar rules to them. And there's different types of grammars that can be applied to generate different types of formal languages. And you could do a whole project on that subject. Then once we get into learning about theoretical machines, these things called finite state machines, which are sort of like a machine you can draw on a piece of paper. And it's not like a real working machine, but it's more so like well, you could make a real working machine, but it's more so just like a theoretical thing that solves a problem. And one of the first and ultimate theoretical machine is a thing called a Turing machine. And that project has the potential to go a lot of different directions. You could study the history of computer science with Alan Turing and Alan Turing's work during World War II, and his whole story is fascinating and heart-wrenching. But he is widely considered the most, like one of the most important people in the history of computer science. And the Turing machine to this day remains the ultimate model of computing. And there's a lot of sort of philosophical directions you can go with that as well. A Turing machine is sort of like a theoretical model of a computer, and you can learn about what it means to be Turing complete. And there's this question as to whether or not a human brain is a Turing machine. Like, can you model a human brain with a Turing machine? And if you can, then hypothetically, we should be able to model a human brain with a computer once we develop sufficient computing power. So this gets into the idea of like, will it ever be possible, if you want to go this direction with it, there's the philosophical direction of, will it ever be possible to sort of upload your consciousness into the cloud and become a digital being, which is something that sci-fi authors love to write about, right? So yeah, that's kind of a fun topic. So that's it. Those are all the topics I have on here. I'll stop recording now, I think. What I want you to do is basically think about which topics you are interested in and send me in an email your top 3 topics, as well as if there's any classmates that you specifically want to work with for the project. Okay, so rank your topics. 1, 2, 3. Or if you have another topic that's not on this list that you're really interested in, like for example, Gödel's incompleteness theorem would be a fun topic, just throwing out a name there. I didn't put it on the list, but if you want to study that, that would be cool. And you can, request it if you want. I will approve any topics. I'll have to make it, I have to approve it, but I'm willing to consider anything, pretty much.